Hi there. Here's lecture 21. I'm recording this on Thursday, March 26th, so this is the fourth day of the new term. This is the lecture that in the syllabus isn't supposed to start until tomorrow. I'm trying to stay at least one day ahead of you in this self-paced mode. Yesterday was the drama with the reading quiz problem. By now, you will have known, by the time you see this, that I've given up on trying to get the Moodle quizzes to work. I don't want to belabor that too much here. So I'm going to grade this and talk about it just as I do in class. Okay, so you won't get self-graded on Moodle anymore. It's here. So let me do this. And this is going to be a long lecture again today, so I need to stick to the basics here. You know from the reading, hopefully, that a generator consists of a moving coil in a magnetic field that rotates. Okay, and if you rotate that, you get a signal that comes out, a voltage source that's sinusoidal in time. That's the lecture. Okay, we've seen some things that are exponential in time. Okay, that was RC charging. Okay, that was a time constant tau time constant for an RC circuit. R times C was the time it took for various quantities to come to an equilibrium. Okay, currents and voltages as a function of time look like that. Exponential rise. Okay, that's an exponential. This is the voltage as a function of time. The current as a function of time looks like this: a peak, and then it decays away. Okay, with the time constant, which is R times C. Okay, this is exponential decay. You and I are watching every day exponential growth. Okay, where the number of cases of coronavirus goes not exponential decay but exponential rise. Okay, looks like that. Okay, the time constant for this, the doubling time for 1/2 increase, is about 2.5 days right now. The whole idea about trying to flatten the curve is to make this time get longer. Some of you have been asking me about that. Maybe I'll put together a lecture about that later on in the next couple of days or so. I'm trying to get into steady state here. Okay, but every day for the last week or so, the number of cases in the U.S. has been doubling on a time scale of about 2 to 3 days. 2.5 days. Okay, we're going to see something similar to that for LR circuits. There's a time constant. This is looking ahead a little bit. The time, this is the RC time constant. The L over R time is L over R, and that's the time that these quantities charge and discharge. Otherwise, the behavior is the same. Okay, I'm getting way too far ahead of myself here. So this is a pretty straightforward, just technology question. A transformer consists of an iron core around which wind coils of wire. The symbol for it is a primary that looks like this. Okay, this symbol is going to be the symbol for an inductor. It's also the symbol for the number of turns on a transformer. This is the primary on the input side, and this is the secondary. And what I've tried to indicate here is a secondary that has fewer turns than on the primary side. Okay, so if we get a primary that has more turns over here than here, the voltage that we get in the secondary divided by the voltage that goes into the primary is the number of turns in the secondary divided by the number of turns in the primary. Okay, so if we want to get a higher voltage, for example, this might be 110 volts, and maybe we want a 5-volt supply for a USB port kind of device, like this memory chip here. That's a USB device. Okay, then we would put fewer turns over here than here in the ratio of 5 volts over 117 volts. We call that a step-down transformer, okay? Because we take the voltage and make it go to a smaller number of volts over here than that, okay? Okay, so here's electric generators. Faraday's law makes the world go round, okay? the consequences of Faraday's law led to what people call the Second Industrial Revolution. The first Industrial Revolution was the Steam Age. That's all the machinery that led to those smelly old hot and stuffy summers in England and in parts of the U.S. Now we have transformers and power supplies driven by Faraday's law. Here's the way a transformer works. We have a mechanical source of energy, hydropower, steam, or a nuclear plant, or wind power, making this coil of wire spin around between two pole pieces. Okay, that gives us a voltage that's induced in the coil, which we can make bigger or smaller to transmit power to the power grid. And there's an example here that comes later that shows that. Here's Faraday's law. Last time I had a green pen and a red pen. My green pen died, and I don't have time to go to Starbucks, to Staples to get another pen. So here's the color code I'm going to adopt from now on. I'm going to try and use red for the induced current. So I'm going to draw the induced color this way. Okay, here's the equation, which is minus d by dt of phi sub b. Okay, and I'm going to write phi sub b in red. Okay, so blue. I haven't rehearsed this, and I'm tired, and I want to get back to teaching instead of doing all this shenanigans I'm doing. So phi sub b is going to be the blue color. This is going to be the source term in some sense. This is the cause. Faraday's law takes a source, which is the time rate of change of a magnetic flux. This is the cause, C-A-U-S-E. And this is the effect over here. This part here is the effect, the induced. Okay, this is the induced. These are all words I'll use interchangeably. This is the effect. This is the cause. This is the effect. This is the source. This is the induced. Okay. Time rate of change of the magnetic field. The flux is B times A times the cosine of theta, and usually that's just an angle that varies. But now if we spin that angle continuously at some constant speed, we don't care what the initial value is, then that's a time-varying flux. That gives me a time-varying voltage. Okay, so there's the red effect because of that blue source term over there. Here's the voltage out of an AC generator. It's sinusoidal. I'm not going to talk about DC generators, okay? Here's how a transformer works. Here's an iron core, okay? And with this symbol that I draw there like that or on the previous page, here's the kind of the physical picture of it. It's a soft iron core around which I wrap a number of turns of wire to make the primary, a number of turns to make the secondary. Here I've suggested there are more turns over here than there are here. So this, as I've shown it here, would be a step-up transformer, okay? So I get more voltage here than I get there, okay? What is that iron core for? That iron core is there for technology reasons that I'm not going to talk about much, okay? Basically, it makes sure that all the flux that comes out of here goes into there. Soft iron sucks in magnetic field lines, so we don't waste any of the field lines that would go out there. From Faraday's law, the number of the voltage induced here in the primary is the number of turns in the primary times d phi sub b dt. Faraday's law, we apply Faraday's law twice. The voltage in the secondary is the number of secondary terms times the d phi sub b dt. With that iron core, these two quantities are the same. We transmit all the change of flux here into this change of flux here. So I take the ratio of this divided by that, okay? And if these are the same, those two things cancel, and I've written this upside down here, I see, okay? This says V secondary over V primary is N secondary over N primary. This is, I wrote it upside down here, I just realized that, okay? So that's the transformer equation, okay? Here's a telegraph. This is a bread and butter result, okay? Every MCAT, every LSAT, not LSAT, every GRE will have you work a problem with the transformer equation. It's a step down transformer if the number of turns in the secondary is less than the number of turns in the primary. That means I have less voltage on the output than on the primary. It's a step up transformer if I have more turns over here than there, and I get a higher voltage on the secondary than there. Okay. Now, this thing is transforming voltage. It also is transferring power, but the power stays the same on both sides. I can't make or destroy energy, but I can lose some energy as heat. Okay, so if I say the primary power is the same as the secondary power, the primary power is the voltage times the current in the primary. The power in the secondary is the voltage in the secondary times the current in the primary. Okay, that tells me this equation here, which is also a bread and butter equation. Okay, if you have no losses in the system, then I get this equation here. Primary power is secondary primary losses. If I get some losses, some heating losses, okay, then I lose some of the primary power, and I get less power here than I get there. Okay, the efficiency throwing away that losses is this secondary power divided by that. Real transformers are not 100% efficiency. The losses are in heat, and I'll show you later on a video of a power transformer explosion. If you're in a big city in the summertime and everybody's running their air conditioning, the grid demand for power gets extreme. All the transformers, some of which are 30, 40, 50 years old, get overheated and they blow up. Okay, if you've ever been walking down the street in the summertime with a lot of power being used by air conditioning, you might see a transformer explode on the pole that's in your neighborhood. That's because of those effects. Okay. Here's an example. Here's an example of this, the power losses in this little gadget here. This is the same transformer. Everything that you plug into the wall, every piece of electronic equipment has a transformer in it. Sometimes they're tiny little things. This one has a pretty good sized transformer. Transformers go from little tiny things. I don't have my demo kits that are in the storage room at Furman, so I got what I got. Okay, to bigger transformers like this in big audio systems, to transformers that are the size of a house and bigger in the transformer yards. If you look at the next time you get back to Furman, hope that's soon, go down to the lake, go down to the utilities area where the shops are, and look at that big transformer yard. You'll see some big transformers there. Here's an example that I made up because I didn't like the examples in the book. Okay, this has 120 volt AC on this side here. That's where I plug this into the wall. Okay, and coming out over here on the other end of this thing is the output voltage. Okay, and this is a kind of an unusual thing because it's just a transformer. A lot of your power supplies for your electronics, for your iPad and stuff, have a DC conversion, but this just I'm sorry, this does have DC out. Okay, so I'm giving you the AC ports inside. Okay, so I've taken that part of it. Okay, I have 120 volts. I don't want that much voltage. I want 12 volts over here for my electronics. How many turns do I need to have in the secondary? If I've got 400 turns there, since I've got a smaller output voltage, I get a smaller number of turns there. So I take that. Okay. It says I want a load of 0.5 amps. That's a half an ampere. What's the current in the primary? The current in the primary is a lot less, okay, because power is current times voltage, current times voltage, okay. If I have low voltage and high current, here I get high voltage, low current to make it the same, okay, and to work through all these things. This thing says that so the input power here, the input power is 18 watts, but I only get 6 watts out. That's that number times that. Okay, so this is only 33% efficient transformer. Okay, don't worry about this business here. Okay. Why do we care about these kind of things? And why do we have transformers in the world? This is a very good example. This is example 29-26 in the textbook here. And it shows you kind of starting from a great big power plant somewhere, a coal plant, a gas plant, a nuclear plant, okay? starting from here and ending up in the house where you're sitting right now, okay? In this house, we want 120 volts AC, okay? Or 240 volts AC. Your house, the outputs you have are 120 volts, but you have two phases, one up and one down, so it's really 240 volts, okay? We could send that power at 120 volts, but we'd lose massive amounts of energy if we did that. So what you do is you take a pretty high voltage source from the power source itself, from the transformer grid. Even that's not high enough. We step it up to a really high voltage, okay? These high voltage, you see high voltage transmission lines all over the country. You want 120 over here, but that power is shipped to you at something like 240 volts, 240 kilovolts, a quarter of a megavolt. What do? Then we take that, when we get close to your neighborhood, we step it back down in two steps to an intermediate power station, 2.4 kilovolts, 2.4 kilovolts, and then we step it down again in your neighborhood with a step-down transformer to 240 volts. What a whole bunch of fiddling around. We step it up and we step it down. Why do we do that? Okay, we do that to save losses in the system. Losses in the system. We ship it at a quarter of a megavolt. We use it down at 120 volts or 240 volts. I'm already up to 16 minutes. You can read this on your own. It's very straightforward. Okay, how much it is with the way we do it in real life now, how much we would lose if we did it at the household voltage. Huge losses. Read that on your own. Okay. I'm going to skip this. Okay, this introduction here to 29.7. You can read through this. Okay, this is mostly just a review of older material because I want to, I'm not going to talk about this. Okay. Let me say no, I just don't have time, okay? Maybe we can do this in a Zoom session because I want to spend the remainder of this video lecture time talking about a very important qualitative question, okay? Here is the question back over here, and here's the answer, okay? You may want to make yourself some extra copies of this thing here to play with so that you can try this on your own. Here's another telegraph, okay? I told you that this problem here, some of these previous problems here are bread and butter problems for calculations and transformer problems. Here's a bread and butter qualitative question, okay? And it has to do with induced currents directions, okay? And you use the right-hand rule twice, okay? And you got a 50-50 chance of getting it right both times. So if you do it carefully, you'll get it absolutely right, okay? Here's the question. Here's the primary of a transformer. So here's a primary here, and here's a secondary over here, okay? I have a current going in here. This is the external source. This is the source. This is the blue thing. So everywhere I have this I external, I'm going to draw that in blue. This is I external, okay, which is going around here, going around here, going around here, going around here. You need to know two things. You need to know the direction of the primary current, okay? In this case, it's counterclockwise. You need to know that, and you also need to know what's happening to the magnitude of the external source current. In this particular example, I sub t goes that way, but it's getting bigger and bigger in time. So it's going 5 amps this way, then 10 amps, 20 amps, 30, 40, 50 amps. It's increasing in magnitude, staying in the same direction. Okay, that's the applied current. That's the external current, okay? Here's what the problem asks. What's the direction? That's all it asks. Not magnitude, you can get that from the numbers. What's the direction of the current induced in that? And there's only two possible answers, and I'm going to draw this in red. Is it clockwise or is it counterclockwise? If you guess, you get a 50-50 chance. Let me show you how to get it right. Okay. Here's the primary, here's the secondary. I wrote those words there. I just now saw that. Okay. Here's how you solve this problem. I'm up to 20 minutes. That's okay. 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 So here's the blue part. Here's the I external. How would we affect the question? This says current's flowing that way and it's increasing in time. Okay. I put a positive battery here with a switch. Okay. That makes conventional current go from the positive around here back to the negative once I close this switch here. Okay. But it's increasing in time. Okay. It doesn't come to the full current right away. It asymptotes with exponential decay times, just as RC times come to equilibrium. Okay, so the magnitude is getting bigger. Okay, here's the external current. It's going this way. I wrap my fingers around the wire here, and my fingers point into the page over here, into the page here, and out of the page here, out of the page here, out of the page here, and all the way around. It's into the page, into the page, into the page, and out of the page, out of the page, out of the page. Faraday's law only applies to what's going on inside this loop and inside that loop. Okay. Okay. Now, for Faraday's law here, I need to worry about that. But over here, I want to know the magnetic field inside this loop. So I've told a story there. Now that's scene one of this problem. Scene two says, what's happening over here? And what's happening over here is there's some blue magnetic field going into the page, okay? And that's the source term from these guys here. Those field lines from this coil here are ending up over here, okay? They're into the page inside this coil, okay, and they're getting bigger with time, okay. Here's a loop of wire. Here's a loop of wire. So now I'm going to apply Faraday's law inside that loop. And here's what Faraday's law says, as I told you last lecture. Faraday's law says I've got some flux inside here due to an external field. And it's getting bigger and bigger in time. The flux is getting bigger. Faraday's law says, no way. I don't want the flux there to change. If the flux is getting bigger in time, I want to induce a magnetic current and some magnetism that tends to counteract that. So inside this coil here, I get an induced magnetic field that goes opposite to the incoming magnetic field external, okay, going that way, okay. Now it goes into the page over here, but I don't care what's going on outside there, okay? I don't care what's going on inside there, outside there, only inside, okay? That means this magnetic field has to be coming out of the page. That means the induced current has to go that way. I put my thumb over here along the direction of the current, and I have to make it go that way to make these little red guys go that way. That means this current has to be counterclockwise here on this one here, okay? Does that make sense? It's like those practice problems from the previous lecture that we had, okay? Look at that, reread the textbook, look this over, make a couple of blank copies of this one, and practice going through that story. It's a storytelling exercise. It's got two scenes. It's a narrative. It has a beginning, a middle, and an end. You're the author that writes a story about Faraday's law. Faraday's law, Lenz's law, another word I told you for Faraday's law, having to do with that minus d phi sub b dt, okay, that's epsilon, EMF over here. That little minus sign is the part of this thing that is sometimes called Lenz's law. Okay, wow, I'm up to 25 minutes. These lectures are clearly going to get longer and longer. Hope you guys are doing okay. We've got, I sent you an email last night about scheduling a Zoom session sometimes tomorrow. The way I'm recording these things now, I can't do picture in picture, so you don't get to look at my ugly face. That's probably a blessing. So I say goodbye to you. I'm sorry for all the screw ups here at the startup. We're 4 days into this. This is the third lecture. Hopefully it'll get better now, and we'll be able to set up some Zoom office hours so that you can talk to me on one-on-one. I haven't heard back from the students who were hoping to do the tutoring sessions and as well as my times, but hang in there, stay safe, stay healthy, and start sending me emails about ways we can make this course better. We'll do that in Zoom tomorrow. Adios, amigos.